Good day. In this lecture, I will teach you step by step how to program the forward kinematics in Python through VS Code here in our virtual machine. Okay. So first, let's go to our home folder. So this is what's inside the home folder. Okay. We will create our own folder here through our terminal. Okay. So let's name the folder Cara V3. Okay, then enter. So the folder Cara V3 is already here inside our home folder. Then next, we will go inside this Cara V3 using the command cd Cara V3 slash enter. Now we are inside our folder. Inside our folder, we will create three folders. First is the kinematics. Next, the RTB or robotics toolbox. And lastly, the Tkinter folder. Okay. We can go back to our folder, home folder, then look inside our SCARA V3 folder. We already inside SCARA V3 folder, we have the kinematics, RTB, and Tkinter folder. Okay, so let's go back to home folder. Next, let's go back to our terminal. We can use the command ls in our terminal to see what's inside our SCARA V3 folder. Okay, then we will go inside the folder of kinematics folder. Okay, using again the command cd, then the kinematics directory. Okay, we are now inside the kinematics folder. If you will run something inside run the program inside the kinematics folder, okay, we will just type the command here in the Terminator terminal. Okay, now let's go to our virtual studio code to start our programming. Okay, let's close this. Okay, and let's go to file and open folder. Okay, let's go to home and find the SCARA V3. Then click open. Okay, now we are inside our SCARA V3 folder in VS Code. What we will do here, let's click this. Let's click the kinematics folder. Okay, in VS Code. Then let's add a new file. Let's click this. Then the name of the file will be fkim.py. So this is a Python file. That's why it's in .py. Okay. So this is our workspace. We will do our programming here. Let me just adjust the layout or the appearance, okay, of my workspace. Okay, so this is fine. So what we will do here is to create a code that will compute the forward kinematics of this Scaravitrary mechanical manipulator. Okay, using the parametric table and the homogeneous transformation matrix formula from the DH notation. Okay, so what we will do first is to import numpy np, then import mat. So we may test if this library is properly installed, let's just save what our coded here in our workspace. Then let's go back to Terminator and test it. So let's hope it is the libraries are properly installed. So Python 3, the name of our file, so fkin.py. So this is what you will type to run the Python file and enter. And if there is no error, you may continue the coding. Okay, let's go back here. So what we will do first is to declare our variables. Our first variables are the link lengths, and let us declare that those variable is in a millimeter unit. Okay. So our link length variables are the a sub 1, a sub 2, a sub 3, a sub 4. Okay. So a sub 1 is our first variable. So what we will do here, we will make a system or code that will make Python ask us what value we want to input for the variable a sub 1. So using the input code or input command, then close open parenthesis, inside the input close open parenthesis will be a string message that will be used by Python to ask us what is a sub 1. Okay. Then we want a float data or decimal data. So we will use the float, the float command that will allow us to input decimal type of data. Okay, so we will copy this and paste 3 times. Okay, this is A2, A3, A3, this is A4, and this is A4. Okay, next to it is the joint variables, okay, which is if b and degrees if theta. Okay, we have 3 joint variables in our kinematic diagram. We have d sub 1, theta 2, and theta 3. Okay, so d sub 1 will be our first joint variable. We will do also what we did in our link lengths. Okay, the Python will ask us if what value we want to input in our joint variable. Let's just rename this t sub 1, and let's copy this 2 times because we have 3 joint variables. Then change this variable to t2. T2 will be our theta 2. Okay, change this to t3, then t3. Okay, next, Python, like MATLAB, doesn't understand the rotation angle if its unit is in degree. So we will convert it from degree to radian. Okay, so Python just understand radian unit. Okay? So to convert this, we will have a conversion factor, and our variable, which is t2, that will be divided to 180 degrees, then multiply 2 NP dot pi. Okay, then the same with t3. This is d3. So now we have a conversion from degree to radian of our joint variables. Then next, we will put here the parametric table. So that will allow us to have an automatic substitution of these variables, of value of our variables to our parametric table and to our homogeneous transformation matrix. Okay, so this is about the parametric table. Okay, so we will put it inside a variable pt. Okay, to create a table, we will use a square parenthesis, then inside the square parenthesis, another square parenthesis. This square parenthesis, inside the square parenthesis, will represent the row. So because we have 3 rows in our parametric table, we will put 3 rows. Okay, and let's bring them down. Just make them align. Okay, so our parametric table at row 1. Okay, I forgot to put what will be the syntax lookalike. So this is theta, alpha, r, and d. Okay, these are parameters, our 4 parameters. So the first row, parameters are 0 degree, 0 degree, 0, a1 plus d sub 1. Okay, so we will put here 0, but instead of just 0, we will make a conversion from 0 degrees to 0 radian. Okay, just to make you always remember to convert uh, rotation angle in degrees to radian. Okay, we will not ever forget to convert. Okay, from degree to radian. Okay, next. Okay, so we have. Okay, next is 0 degree also. Let's just copy this for our alpha. Okay, next is R, which is 0. Then our D is A1 plus B1. Okay, next, we have here an error. Said it was not closed. It was not closed yet. Sorry, I forgot the multiplication symbol. Okay, next is row 2. Okay, this is row 2. We have here theta 2, 0 degrees, A2, and 0. So we will put here the T2, which is already converted above here. It is T2. So it's already converted. Okay. Next, 0 degrees. So let's just copy this alpha here. It's also 0 degrees to 0 radian. Again, even though it is 0, I will convert it to 0 radian, okay, to make you don't forget that we need to convert from degrees to region. Then next, what is our R? Our R is A2. Then our D is 0. Okay. Okay, last for row 3. Row 3 is theta 3, then 0 degrees, A4, and A3. We will put here T3. It's already converted to region. Then 0 degrees, alpha. Okay, let's copy this. Then our R is A4. Then our D is A3. Okay, so this is our parametric table. Next is our homogeneous transformation matrix formula or formulae. Okay. So we will, because our parametric table has 3 rows, it means that we will have 3 homogeneous transformation matrix: the H01, the H12, the H12, and the H23. Okay, so our first variable will be H0 underscore 1. Okay, then we will put here our homogeneous transformation matrix formula, which is this. Okay, for row 1. So to create a matrix, just like how to create a table, we will put first a square parenthesis. Inside the square parenthesis, another square parenthesis. The square parenthesis will represent the row of our matrix. So the homogeneous transformation matrix has 4 rows. So we will put 4 of it. Okay, next. Let's align them. Okay. So for row 1, we will put this cosine theta, negative sine theta, cosine alpha, sine theta, sine alpha, Rn, cosine theta. Okay. So the theta, alpha, R, and D will be extracted from our parametric table. So we are at our first row. Okay. The H01. This is the first row. We will extract the values of our parameter theta, alpha, R, and D. Okay. So using the row per column, okay, or row by column data of our parametric table, we will extract the the elements of our parameter and substitute it automatically in our homogeneous transformation matrix. Okay, so let's go back. So our first data is the cosine theta. So it is NP cosine, close open parenthesis. So inside here is the variable PT we use in our parametric table, and the location of the value of the theta, which is 0 degrees. Okay, in our parametric table, it is located in the 0 by 0 position. Okay, or the 0 by 0 element. Okay, because this is a Python programming, our counting will start from 0. So it means, okay, per column start from 0 to 3. The numbering, it will start from 0 to 3, and our row will start from 0 to 2. Okay, so our 0 degrees theta here is 0 by 0. We'll put it in here, 0 and 0. Next, okay, the next one in our homogeneous transformation matrix. Okay, the next element is negative sine theta cosine alpha. Okay, so this will be negative and p dot sine close open parenthesis pt. Okay, so this is theta. It means the row is 0, the column is also 0. Then there will be cosine, so it will be multiplied to np dot cosine. Just close open parenthesis. We need here the data of alpha at row 1, the data at the data of alpha at row 1, okay, is at element 0 and 1. Okay, 0 and 1. So this is how you will extract, okay, extract data from the elements of your table. The same rule applies to matrices. Okay, so we will have three of these homogeneous transformation matrix. We will have another two of these homogeneous transformation matrix for x12 and x23. Okay, but because the formula is too long, we will do something to make it easy for us to copy paste this. So we will assign a variable which is I, and inside this variable is the row 0. Okay, 0 came from the number of row from our parametric table. So if we will copy paste this, we will just change the value of I. Okay, we will change it to 1, I equals to 1 for the next row of our parametric table. Then the last homogeneous transformation matrix, we will change the value of I into 2. Okay, then we will change the row element in our homogeneous transformation matrix so that I will feed the value of the row in our homogeneous transformation matrix. Okay, so after this, the next element has sine theta and sine alpha. So np dot sine, open parenthesis. So this is theta. This will become I0. Okay, row 0, column 0 times sine alpha. Okay, will be multiplied. It will be multiplied to sine alpha. Okay, so np dot sine, open parenthesis, pt square parenthesis I1. Then the last element in our first row is r cosine theta. Okay, the element of r is at row 0, column 3, or sorry, column 2. Okay, so this will be pt square parenthesis I2 multiplied to, sorry, have here Okay, multiplied to cosine. Okay, multiplied to cosine. Sorry, np dot cosine. np dot cosine. Close open parenthesis. pt square parenthesis I 0. This is theta. Okay, let's look again. Okay, this is theta, cosine theta next. Row 2, so this is sine theta, cosine alpha, negative cosine theta, sine alpha, arc sine theta. Okay, so what we will do here, make it faster, we will copy paste this and put it in here. Okay, and just change some functions, some trigo functions. So this is cosine. Okay, this is also cosine theta, so it will not change the data of our the data of our row by column. Okay, so wait a minute, we have an error. Okay, we have an error right here. Okay, there's an error. There is a squiggly line. Okay, I just removed it. So this is cosine theta, cosine alpha. The next is negative cosine. So this is negative cosine theta. So we will not change the row by label data. Then next is np dot sine alpha. Then this will becomes r sine theta. R sine theta. Next, okay, our row 3 is 0 sine alpha cosine alpha d. So this will become 0 np dot sine close open parenthesis pt square parenthesis and square parenthesis. So this is alpha. So the element is 0 by 1. Next, np dot cosine close open parenthesis pt square parenthesis square parenthesis. So this is element alpha or parameter alpha. This the element is 0 by 1. Okay, then the last data is from d. So d is at row 0 column 3. So what we will put here, pt square parenthesis I and then 3. Okay, next, the last row will be 0 0 0 1. Okay, put here 0 0 0 1. Okay, our homogeneous transformation matrix from row 1. So now we will copy and paste it 2 times. Okay, so copy, paste, then paste. Then let's change the value of I. So this is for row 1 and this is for row 2. Let's also change the name of the variable x12 and x2 sorry. Okay, so this is the homogeneous transformation matrix formula. Okay, so now we have the formula for our direct substitutions and yes, for our direct substitutions we will print them. Okay, we will print first the x01 matrix. Okay, but we will convert it again into matrix using np.matrix, because what we have done here is we created a table but not a matrix. Okay, so to make it a matrix, we will convert it first into matrix. So np.matrix, our variable x0 underscore 1. Then we will create, or we will print a string message telling us that this is x0 underscore 1. Okay, then we will print the x0 underscore 1. Okay, so we have another two of these. We will copy paste it and just change the variables. Okay, even the string message. So don't forget to change the variables and the string messages after copy and pasting. This will be 2, this will be 3, this will be 2, this will be 3, okay, 2, 3, 2, then 3. Okay, now we will already created uh, a program that will print the matrix. Now we will create a program that will multiply these three matrices, the H01, the H12, the H23, to have the homogeneous transformation matrix of the mechanical manipulator from frame 0 to the end effector frame 3. Okay, so we need this homogeneous transformation matrix, this H03, to describe both the rotation and the position of our mechanical manipulator, so that we will know where will it position, or where will it move, and how will it angle in space, or how will it orient in space. Okay, so to multiply it, have those three multiplied. We will use the np dot command to dot product them. Okay, we will dot product them instead of just multiplying them. Okay, so we will dot product first, or multiply first the x01 and x12, that will result to the variable x02. Okay, we will do it like this because the np dot can just accept two matrices. Okay, or two variables. It can just accept two variables. So we will put here the x01 and x12. Then next, we will now multiply the x02 to x23 to have h03. So x03 is the final answer. Okay, or the final homogeneous transformation matrix. Okay, we will use the np dot, then multiply x02 to h23. Okay, then before printing it, we will create a string message to let us know that this is what we will print is the x03. Okay, last we will print x03. Okay, but this x03 is not a matrix, but because if you multiply using a dot product, you will convert it into scalar. So we will convert it again into a matrix. So np dot matrix, close open parenthesis, Okay, so it will convert the dot product of x02, then of x02 and x23. And also, I want to have a matrix that has a decimal number that is round off in 3 decimal places. So using the np dot around, okay, using the np dot around, putting here in 3 after a comma, our final answer or our final matrix will have decimal elements or decimal data, but 3 decimal places or round off in 3 decimal places. Okay, so let's save this, Control S, and let's check first if there's an error. Okay, let's check if there's an error. Be careful with the commas and the parentheses. Okay. So if you're really into robotics and programming, you will be cautious with the commas, the parentheses, the colons, the semicolons, okay, and the syntaxes, okay, of your functions or code. Okay. Now let's go to our Terminator and run the program by using this command, Python3, the name of our file, then .py, and enter. So what this do is it is asking us what will be the value for our link lengths and then the joint variables later. We will use these values, okay, for our test. Okay. A1, A2, A3, A1 is equals to 10, A2 is equals to 10, A3 is equals to 5, A4 equals to 10, B1 is equals to 5, theta 2 is equals to 30 degrees, and theta 3 is equals to negative 45 degrees. Yes, so let's put it. So 10 degrees, 10 degrees. If you put a value that is wrong, you may press Ctrl C to start over. Okay. Again, Python 3, fkim dot py, enter. So 10, 10, then 5, then 10, then D1 is 5, theta 2 is 30 degrees, then D3 is negative 45. Okay, so we have here now the homogeneous transformation matrix. The final answer is here. Okay. So this is our homogeneous transformation matrix H03. So this is the final answer. Okay. So let's check again. I think there is something wrong with this. And I think there is something wrong in my computation. Let me just check it. So this is A2, T2. I've got the wrong answer. So let me check first. Okay. Sometimes you will not it's hard to locate the wrong answer. Okay. np.cosine. Wait a minute. We just look. This is 0 degrees. NP 0. We just check. Okay. R is 0. 820, A483. This R is correct. I think I have a wrong answer at each 2, 3. Yes, I have a wrong answer at each 2, 3. Oh no, it's at each 1, 2. It's at each 1, 2. I think I have each 1, 2. Oh, this is not cosine. This is sine. Okay, sorry, this is sine. Okay, I will provide source code. Okay, so that it will be easy for you to debug this. Okay, so let's do this again. Okay, just write again code Python 3. Okay, then f in the py. Okay, so this is 10, then next 10, then 5, then 10, then 5, and 30 degrees, then negative 45. Okay, so this is the correct answer. Okay, our position vectors are 18.32, 2.412, and 20 millimeters. Well, this is our rotation matrix. Okay, so this is already correct. So I hope you will be able to create this in your VS Code. Okay, thank you.